Welcome back to The Frequency with PUI Audio. I'm Kevin, and today we're going to be talking a little bit more about electrical signals and how you can measure them. This is a DC signal. This is an AC signal. To measure these, we'll start with measuring the peaks in the signal. If we wanted to determine, well, what's the maximum value this AC signal will ever achieve, we look at the voltage peak. The voltage peak is simply the voltage in between your reference, 0 here, and the highest peak. Or if we wanted to look at the negative voltage peak, we simply do the opposite. We measure to the lowest peak of the signal. If we look at this DC signal, well, there is no alternating portion here or here. It may look like these valleys are alternating portions, but they're not. They simply return to 0. They never hit a negative signal. A DC signal will never have a peak-to-peak voltage, known as VPP for short. DC signals will only ever have a 0 to peak signal. These voltages are always changing in an AC signal. In a DC signal, it's pretty obvious that at this point in time, your voltage is here. At this point in time, your voltage is here. It's always the same voltage. In the AC signal, this wave is continuously changing. Here is a different voltage in time than here. So how do you represent that entire signal? You use what's called Rms voltage. RMS stands for root mean squared. The name comes from how you derive the formula, which is well beyond the scope of this video. All you need to know is that RMS equals 0.707 of the AC volt peak signal. To further clarify that, 0.707 of your voltage peak lies around here. That means about 70% of your signal can be described with whatever RMS voltage you calculate. That's not to say that it is the average signal though. The average signal of an AC signal is 0. The positive peaks always cancel with the bottom peaks. They alternate and they're always equal. RMS voltage is generally used to measure most signals. In fact, unless otherwise stated, it's a good bet to assume you're measuring RMS voltage. Most meters and oscilloscopes will have the option to either switch between them or it'll be measuring RMS by default. So these three measurements describe the amplitude of an electrical signal, meaning how tall it is when it's represented by the graph. But you might be asking yourself, how do I describe how fast it goes? AC and DC travel at a frequency, a term you've probably heard of. Frequency is expressed in hertz. Hertz are defined as cycles per second. We're going to use a very simplified example. If this AC signal was traveling at a rate of 1 cycle per second, the time it takes for it to cross that axis again, giving it 1 full cycle, equals 1 second. This gives us a frequency of 1 hertz as it cycles 1 time per second. The time period has an inverse relationship with frequency, meaning your frequency equals 1 divided by your time period. In real-world applications, these time periods that you measure are going to be much, much smaller, in the domain of milliseconds to microseconds. This means that the frequency which you calculate is going to be much, much higher. Relating this to audio, an audio signal sent through the air travels in a waveform very similar to an electrical signal. In fact, the same calculations hold true. When a human hears a sound, it's between 0 and 20,000 hertz, meaning for a 20,000 hertz signal, the time period is very, very small. These are all basic calculations that you can extrapolate and use in any electrical application needed. Hopefully now you have a better understanding of electrical signals and what comprises them. If you have any questions or you would like us to expand further on anything discussed, leave a comment in the comments section. As always, like, subscribe, and we'll see you next time.